me what is this distance? Anyone?
Can you not just assume that load to be unevenly distributed with a gradient load? Like you
No,
could have a
no.
could
The
you not
function, the function will not be the same.
okay.
You can still solve the problem. Okay, if you just want to solve the problem, yes, but you cannot find the function. Okay. Anyone? What's the distance? I'm going to see the chat. Maybe some of you don't have mic. Verus, yeah, you are right. 2 or 3 length. Sorry, that's incorrect. I like that. It means you know what is correct. I like that. Okay. Yeah. This is not L over 3. L over 3 is only for a triangle. This is not a triangle. It is. Okay. So this okay. So this is not L over 3. So therefore we have to apply. Now this is big word, I'll tell you, okay? We have to, the word is so big, okay? We have to apply superpositioning. Big word, okay? Superposition method. So if you want to scare people away from knowing how to solve a problem, you say this is using superpositioning, and then people, oh shit, it's gonna be difficult. No, it's not difficult at all. So what do I mean by superposition? Okay, superposition means you divide the load into, you divide the distribution into 2 parts. Okay, it's called super. When I read the textbook superposition, I said, oh shoot, it's super. And guess what? It's actually super easy. Okay, so with a load like this, it's basically equal to a load distribution that look like this. But you have to be careful, yeah. So this is still 6,000. This is 18,000. So this load over here is 6,000 Newton per meter. And plus, so why we divide it this way? Because like Sean mentioned, right, the evenly distributed load, we know where the what, where the position of the equivalent load is. And then the next one, as you guys have guessed, this will be equal to a gradient load. And this gradient load will start from 12,000. Because 6,000 plus 12,000 is your what? Is your bleh, is your bleh, 18,000. Okay, so this is evenly distributed. This is gradient distributed. Okay, so finally, to get the equation, you have to what? Summation of shear force. Equation is V, I call E for evenly distributed, okay, as a function of x, plus by V, and I'll call this G as in gradient distributed as a function of x, and then summation about moment as a function of x is equal to moment for E as a function of x plus by moment of G as a function of x. Okay, so I'm just going to quickly solve it. Okay, mathematically, the evenly distributed load is easy. Okay, the even you guys know this. Okay, let me divide my page into 2. Okay, so this one side is for evenly distributed. We're going to apply our own method that we know. Okay, so evenly distributed on this side. So I'll put in evenly distributed. Okay, so you have, so we have as a function of x, right? So this over here is 6,000 x. Distance from here to here is x over 2. V as a function of x. M as a function of x. Okay. So this is where our point A is. Okay. So we apply static analysis. This will be equal to 0 and minus 6,000 x minus v as a function of x. So v as a function of x is equal to minus 6,000 x. Then we take moment as a function of x is equal to 0, means we're going to take moment over here. So what we have is same direction, so 6,000 x squared divided by 2, right? And then we plus by m as a function of x. So m as a function of x, okay, is equal to minus 6,000 x squared over 2. Okay, so this is for evenly. Okay, so I'm going to put v evenly distributed as a function of x, and m okay, right? So the next one we're going to do, so evenly distributed is easy. Okay, it's really straightforward. Then the next one we have to find. Now I need you all to focus on the gradient distributed load. Okay. So on the gradient distributed load, right? We cannot just do half base times height on this. Okay, we cannot do that. Okay, because the equivalent load as a function of x has to be a function. Okay, so what do I mean by that? So for this case, you have to do the function first for the gradient. Now, as I said, I need you all to pay attention on this. Okay, the evenly distributed, you can sleep. This one you have to wake up. Okay, hey, wake up. Okay. Okay, I need you. Okay, so this is distributed load. So we have to find what is omega as a function of x. Okay, so we know this already, right? So omega as a function of x, right, is equal to 12,000 divided by 6x. So this is our 2,000x. Okay, this is a 2,000x. Then the equivalent load is equal to you have to integrate omega as a function of x dx. Okay, and we know, right? We know we're going to integrate from 0 to x. Is, as I say, is a function of x, right? So this will be equal to, I'm a bit tongue tight now. So our equivalent load will be equal to 0 to x 2,000 x dx. So after you integrate, is equal to 1,000 x squared. Okay, 1,000 x squared. Okay, does that make sense? Okay, let me not skip steps. Okay, so it's equal to 2,000 x squared divided by 2. Okay, so it's 1 by 0 and x, so this is equal to 1,000 x squared. Okay, now we cannot just say, okay, we cannot just say, okay, I know this. Okay, so for this case, it's just half multiplied by base multiplied by height. What is the height? Right? You cannot just do that. You have to do it as a function. Am I right? Does that make sense now? I know if it's n to n, if it's from one end to the other end, when it's 0 to 6, yeah, you can apply half times base times height, right? Half times 6 times 12,000. You can do that, okay? But this case, you can't, because you don't know at a certain x what is the height. You don't know. That's why you have to form as a function. Does that make sense to all of you, please? I'm not hearing anything. It's worrying now. Hello? Are you all clear with that? Okay. Now, regardless whether evenly distributed or gradient, you already formed the function already. Okay. So let's say for evenly distributed, you know this is 6,000, right? And you know that this is 6, right? And this is x. So to form the equation, right? To form this equation is basically what? So this is a flat line. Yes or no? So your omega as a function of x is already what? 6,000. Then when you integrate, that's where you get what? That's where you get your 6,000x. Okay, you have done this unconsciously. Okay, you just take it for you just use the normal practice. You know that it's a flat line. That's why you put 6,000 times x down here. Now, from here, right now we know that. Now we can start using our what we have known before. Okay, so this is as a function of x. So we know now the equivalent load is 1,000 x squared. Now we know that the distance from here to here is x over 3, right? So, and then we know that this is b as a function of x, and then this is m as a function of x. Okay, then we can proceed. Okay, so summation of forces in the y direction is equal to 0. So we have our what? We have our minus 1,000 x squared minus b as a function of x, 0. So b as a function of x is equal to 1,000 x squared, right? And then we can do our summation about moment in the z direction as a function of x. The whole thing is equal to 0. So this will be equal to 1,000, same direction, 1,000 x cubed over 3 plus m as a function of x, right? So m as a function of x is equal to minus 1,000 x cubed over 3. Okay, so this is equal to a v evenly or gradient as a function of x. This is equal to a moment gradient load distribution as a function of x. So now we put all of them together. Yeah, I'm just going to put all of them together down here to save space. Okay. So now we put all of them together. So it's equal to so the first term over here, our v is equal to minus 6,000x, and then the other one is minus 1,000.
Sorry, Eugene, why was the moment 1,000x cubed over 3?
Oh, because 1,000x squared, x multiplied by 3. Force times
Oh,
distance.
okay, thank you.
Okay. So this is minus 1,000 x squared, right? Minus 1,000 x squared, and minus 6,000 x. Okay, minus 1,000 x squared minus 6,000 x, and then you summation the moment as a function of x is equal to minus 1,000 x cubed over 3, and then minus 6,000 x squared over 2. Okay, so exactly the same, right? Exactly the same of what we have, okay, between, so you realize that this expression over here and this expression over here are the same. Only the higher power term, I did not divide, I did not bring it to, or if I mean both of